The factor theorem. If a polynomial can be divided exactly by a factor and the remainder is a 0, therefore the h will actually be the factor for the polynomial. For example, if you have fx as stated below and x minus 4 is a factor, so how do we prove this? We have to divide the polynomial with 4 using syntactic division. When we divide it by 4 according to the syntactic division method, or this is known as the loom diagram, the end resultant here is actually a 0. The remainder is a 0. Therefore, when you substitute 4 into fx, it will result in a 0. This proves that x minus 4 is actually a factor for this polynomial. So to conclude all the factors, x minus 4 is one of the factor for the polynomial, and the remaining of the factor can be obtained from the quotient, which is resultant from the loom diagram. 2, negative 1, 1, 1. So when you divide a quartic with a linear, your quotient will actually be cubic. So this is a coefficient of the cubic, 2x cubed minus x squared plus x and plus 1 plus 0. This shows that the remainder is actually 0. So this concludes the factor theorem. The remainder theorem is actually an extension of the factor theorem. When we divided the previous polynomial with 4, the remainder is actually a 0. So this concludes that when we divide a polynomial with a divisor x minus c, the remainder is actually fc. So from the previous function we saw, when we substitute 4 back into the previous function, we will actually get the end result of a 0. So for example, the remainder after 2x squared minus 5x minus 1 divided by x minus 5 is actually 24. How do we know this? We can actually perform the syntactic division to determine the remainder. However, there is another method which is the remainder theorem, and we are not required to actually apply the syntactic division in order to find the remainder. How do we do this? Is simply by using this theorem here. When we divide a polynomial by x minus c, the remainder is actually fc. So in this case, x minus c, the c is 5. So when we substitute 5 into this polynomial, the end result is a 24. So this concludes to the remainder theorem. So the remainder can be obtained by substituting the divisor value and performing syntactic. So therefore, performing syntactic division is not required in order to determine a remainder. So now we're going to look at the next example, how to factorize fully a polynomial. So for example, if you are given to factorize this polynomial, obviously when you want to factorize the polynomial fully, the remainder has to be a 0. So for example, we will perform the loom diagram calculations. So we write all the coefficients. Before you write the coefficients for the loom diagram, make sure your polynomial is actually arranged in decreasing order of the powers of the unknown. See 3, 2, 1, and 0. So therefore, you write the coefficients accordingly, and you try to guess a root for the polynomial. This 2 is actually a guess, so you can look at 6. There are some tips to guess it. 6 is a multiple of 1 times 6, 2 times 3, or 3 times 2. So therefore, maybe we can guess 2 as one of the root. So once we guess the root 2, we actually perform the loom diagram method. So 2 brought down, multiplied by 2 is 4. Negative 11 plus 4 is negative 7. Negative 7 multiplied by 2 is 14. Negative 14, sorry. Negative 14, you add with 17, you actually get a 3. 3 times 2 is 6. And here will actually give you a final result of 0. So therefore, x minus 2 is actually root for this polynomial, and x minus 2 is actually a factor of this polynomial. So remainder 0, so x minus 2 is a factor. So therefore, how do we actually write out the answer when we want to fully factorize a polynomial? The original polynomial equals to the first root, so we since 2 is actually the root, so x minus 2 is a factor. And the quotient actually will give the remaining of the factors, which is 2x squared minus 7x plus 3. Please be reminded, if the factorized, the original polynomial is x to the power of 3, and we divide it with x minus 2, so therefore the power of the quotient is reduced by 1. So that's why it's x squared, x, and also 3. So when we can factorize this simply by using our scientific calculator, and this will be the end result. So the polynomial here is fully factorized, and this will be the final answer. We will look at example 2. How do we actually fully factorize a polynomial? So in order for us to guess the first root which we want to divide with, we can actually use our scientific calculator and determine the first root from the calculator. So for example, using the scientific calculator, I actually got a root of -1, because -8 can be a resultant of -1 multiplied by 8. And I make sure that the power of the unknowns is arranged from highest to lowest. So it's in other terms, it's decreasing. And I write all the coefficients of the unknowns. And I perform the loom diagram calculations. 1 down multiplied by -1, you get -1. And add these two, you get 2. Multiply by -1, you will actually get -2. And -6 add with -2 is -8. -8 multiplied by -1 is 8. So therefore, your remainder will be again a 0. So therefore, this is a proof that -1 is a root for this function, and x plus 1 is a factor for this function. So please pay attention. X equals to -1, and when you bring over the -1, it becomes x plus 1 as a factor. So this is a root, this is a factor for the polynomial. So how do we write it? As a fully factorized polynomial function. So one of the factor is x plus 1. The remaining factor can be obtained from the quotient. So in this case, it will be x squared plus 2x minus 8. And then we can further use the calculator, the scientific calculator, to factorize this. And will give you a result of x plus 4, x minus 2. So therefore, this polynomial is fully factorized. Now we will visit another example. Find the value of a given that x minus 3 is a factor of this function. Hence, factorize the polynomial fully. So how do we actually find the value of a? We can use the synthetic division method. So if x minus 3 is a factor, and then the remainder has to be a 0. So now we're going to find the remainder in terms of a and solve it by equating the remainder to 0. So in this case, 1 came from the coefficients of x cubed and x squared, and a is the coefficient of x, and minus 12 is the number here, divided by 3, because 3 is a factor. The end result here has to be, the remainder has to be a 0, because this is a factor of the polynomial. So we perform the synthetic division as usual, using the loom diagram. So bring down the 1, multiply by 3, you get 3, 1 plus 3 is 4, 4 multiplied by 3 is 12. So a plus 12 here, and a plus 12 multiplied by 3, 3a plus 36, and then you add both of this. This will actually give you the remainder. So therefore, we add these two. This will actually give you 3a plus 24. So this will actually equal to 0 because x minus 3 is a factor according to the remainder theorem. So therefore, we equal it to 0, and then we solve the a. It's actually -8.